Today we won't have a live lecture because I have a time conflict in the afternoon, but I will record this lecture and hopefully get it uploaded before the lecture is supposed to start. Yeah, this week we'll be talking about hybridization and scoring. Hybridization just means ways to combine different systems that generally take in different types of data and make predictions based on those. So if you're able to hybridize these, you can exploit each model's ability to deal with a certain type of data and end up with a system that's more flexible and more robust to different scenarios where like one type of data may be present while another is not. So if your model is able to like know in what cases does this system fail and in what cases does the system succeed, then you can sort of adjust how you favor each of the systems in your hybridization to make more flexible predictions. And then scoring is more about evaluating your models, getting numerical scores for how well your model is performing on, let's say, a validation set, and like trying to evaluate how well your model distinguishes between different classes. Right, so just a recap of the types of recommendation systems we talked about in the first few weeks. You have collaborative systems that take community data, you have content-based systems that use product features, and you have knowledge-based systems that use product features and knowledge models. Right, all of them will keep a profile for each user because like the collaborative system needs to know information about a user to group them with similar users. A content-based system needs to know the types of item this user has bought in the past to sort of pair items with this user profile. And the knowledge-based system obviously needs the user profile to understand their preferences and use that information to query from its knowledge model. So yeah, they all take in different sources of data, and they sort of handle the same sources of data in a different way. So you might have use cases where you initially don't have community data, but you initially have product features. In that case, you might want like one solution is to use a content-based system early on and then switch to like a community to a collaborative system. But you can also do it in a smarter way where you sort of hybridize these two models and like increase the weight on your collaborative system over time. And what we're going to talk about today are like different ways to combine these models. I'm gonna skip this slide. This is just you can look at this in the textbook if you want to. It's just a more mathematical way of formulating the recommendation problem, but like it doesn't actually give that much insight into the problem because like each use case is just so different, and that's like any definition you give that tries to capture the problem in general is probably not going to describe anything specific about the use case you're interested in. Yeah, so the first type is monolithic hybridization, where you just have one hybrid recommender take in different sources of information. This is generally what the more modern systems do because like they rely on this neural structure. They're able to learn from a very wide set of features. And we're going to move very quickly through hybridization because it's just like very high level design choices. Whereas later in the lecture, we'll talk about like a more specific system. Yeah, so one thing you can do with monolithic systems is to use content-based information to augment community data. So like if you have interaction history between users and items, that history might be very sparse. So like you might not be able to deduce much about the like you have a set of interactions between users and items, right? But that set is so small that you can't really predict how a specific user will react to a specific item in general, right? In that case, it might help to group these items by category if you have information on what category those items belong to. And like a content-based system obviously would have that type of information, right? Because it has product feature descriptions. And that then if you group items, you essentially get more information about each of the groups, and that allows you to make better predictions of items from those groups to users, right? Because you have more in that way, you sort of have more interaction history per group of items as opposed to individual items where you have very sparse interaction histories. And you can do content boosted collaborative filtering. This means like at the start of your collaborative filtering system, you might not have a lot of community data. So you probably don't have a lot of ratings between users and items. And what you can do when you don't have that information is to use a content-based system to generate these ratings and just fill in your collaborative filtering matrix with these content-based scores temporarily. And then you can like sort of get a working system, because even though it doesn't actually use collaborative information, a content-based system is still going to make somewhat reasonable predictions. And then off of that, you can build more community data and then gradually replace these missing ratings in your matrix. Yeah, and different architecture is parallel hybridization, where you have a set of n recommenders. They each sort of make recommendations independently. They'll each give a score to each item, and then have a hybridization step that combines these scores to make the final recommendation of your entire system. Right, so there are many strategies for this. One is just to mix the outputs of each recommender. That just means you merge all of the outputs, right? So if you have n systems, each makes 3 top recommendations, you'll just output 3 in predictions. This is obviously not very just doing that naively obviously will not give you very good recommendations, because you're giving too many recommendations and you can't really tell which ones are specifically relevant to the user. So you might put on top of this another model that scores the small set of items that you collect from each of the system. And the reason you're able to use a more fine-grained model is because now you've reduced the entire set of items to a very small subset. And in that case, you can afford to use more information about each of these items, and you can afford to make more complicated computations on these. And we'll see more of this later in this lecture. There's also a strategy where you just weight the sums of scores by each recommender, right? So let's say for item I, the first recommender gives you a score of R1, and the second gives you R2, and so on, right? You might combine these scores using some weighted scheme, right? So like you have a weight for the first recommender, you have for each of the recommenders, and you take a weighted sum of their respective scores to get the overall score for an item. So your scores can reflect the weights you put on each recommender can reflect many different things. You might put static weights on them, which means you have a fixed set of weights for each of the recommenders. And in that case, this weight might just reflect the quality of the recommender. Obviously, when you believe it is more capable of making high quality predictions, you put a higher weight on it. But in that case, the limitation is obviously that you might as well just give it a weight of 1 and not use any of the other recommendation systems. But like one reason you still might want to combine it with other systems is because like maybe this best model you have is only capable of recommending items for a subset of the users, and then for the other users you might still want to use your not as high quality but more robust models. Yeah, you also have dynamic weights, which you can adjust with respect to some evaluation metric, so that you find a set of weights that minimizes the error of the system on a holdout set. And you do this because you believe like the holdout set is a reasonable representation of the data that it'll come across in the real world. So like the belief is that if you have a small predictive error on the holdout set, then these weights will be also good in practice. You can also do what's called switching, where you have a so-called oracle model choose a recommender for a specific input. So it basically decides, it looks at the input and decides like which recommender is best able to handle this data. And the reason you might, the reason this might, the oracle is also performing a classification task, but you can sort of see why this classification task is significantly easier than the classification task in each of the recommenders, right? Because it only has to look at the data and vaguely determine like which recommender handles this best, as opposed to the recommender that actually has to make the classification, right? So even if your oracle only relies on some very coarse features, it's still going to do better than if you just had static weights on each of the recommenders, right? So you have a oracle choose which recommendation system to use, and you just use the output from that single recommender. You can also think of this as a special case of dynamic weighting, where your oracle just picks one model to give a weight of 1 and gives 0 to the rest of the other systems. An example of this hybridization scheme. So you might be starting a collaborative filtering system, but you have the problem of a cold start where you don't have enough community data. So you can use, in that case, you can use a knowledge-based approach to make recommendations and then therefore generate interaction history. You do this until you get enough interaction history to run a collaborative system. And you can use in a different example, you can use a nearest neighbors model on content-based features by default. And you might occasionally run into items that don't have nearest neighbors. So these are items that are very different from the rest of the items you see on the system. And you can't really recommend these items based on their features alone, because there isn't really anything similar in the system. In that case, you can resort to looking at collaborative filtering data and seeing like which users have used this item in the past, and use that information to recommend these strange items that don't really work in a content-based setting. Another less common way is to do pipeline hybridization. So like you'll have each recommender act on the output of the last recommender, and you essentially narrow down on a set of candidate items. And you might also have one recommender compute some features and send it to the next recommender, right? So you don't just have to, so it might not just be narrowing down on the list of candidates. You could also be computing more and more high-level features on these items. Actually, I shouldn't say this is less common, because I guess many modern systems you can think of them as a form of pipeline hybridization, although it's probably no longer the case that you're developing these recommendation systems independently and training them together. It's more like you have a system where like each block just does computes a certain set of features, and you optimize the whole thing together. Yeah, it's like a summary of what we talked about so far. There's monolithic designs that you have a single recommender that integrates many sources of information, and you engineer these features in a certain way that makes them compatible. And like one easy way is obviously just to vectorize the whole thing. You have parallelized designs. They're least invasive in the sense that you don't have to modify any of the existing recommenders. You just allow them to predict independently and then combine the outputs at the end. And you have pipeline designs where you narrow down on the set of candidates, and you can also like have each recommender compute different features using different information about the candidate items. So for the next part, we'll talk about evaluation. So generally, there are two big categories of evaluation methods for recommendation systems. There's online evaluation, where you basically deploy your model and test it with real users. And there's offline evaluation, where you compute metrics on historical data sets. right? We'll be focusing more on offline evaluation because it's more like ML focused and more theory. But as a brief, to give you a brief idea of what online evaluation does, one common strategy is just to do A/B testing, where you give a fraction of your users the new system, and you give a fraction of your users the old system, and you collect feedback on which system works better. Then you can determine whether or not your new system works better than the old system by computing statistics on this feedback, right? There are ways to determine if there's like a statistically significant difference in the performance of your new model. For offline evaluation, you usually have a historical data set, and you hold out a portion of that data set. You don't allow your model to see it, and you train your model on the other part of the data, and you have it make predictions and check those predictions against the holdout set. And this is because you think the holdout set is predictive of its performance in the actual in the real world. But obviously the problem with offline evaluation is that especially in recommendation systems, the data you collect sort of depends on the recommendations you're making, because users see your recommendations and then respond to those, right? Their interactions aren't spontaneous. So you might develop a system that does well on the historical data set, but it ends up changing how users it ends up changing the types of things that users click. And it might not, it might sort of hurt its own performance by changing the distribution of data in the real world. Right, so A/B testing is definitely more robust to this sort of behavior, whereas historical data sets might be subject to these problems where it only captures the state of your system at a certain time, at a certain point in time. Yeah, and these are some of the very basic metrics for evaluating predictive scores. Mean absolute error just computes the average deviation between your predicted scores and actual rating. This is for use cases where you have data of the ratings from users on specific items, and your model is asked to predict these scores as opposed to classification, which we'll talk about later. So this just measures how far apart are your predicted scores from the actual recorded scores. Mean absolute error, it just averages over the absolute difference. And root mean squared error, it takes the square root of the average of the square differences. And the difference here is that because you're doing this squaring thing, you place more emphasis on larger deviations, whereas in the mean absolute error case, you only penalize deviations proportionally to how large the deviation is. Root mean square error, it's proportional to the square. Actually, yeah, so you're penalizing larger deviations more than proportional. One example of applying this root mean squared error metric is remember from week 1, we talked about factoring matrices into user and item vectors. We can evaluate how close your user and item matrix resemble the original rating matrix by looking at the difference between their product and the recorded rating matrix. And so one strategy of actually computing the U and I is just to randomly initialize them and then optimize them using gradient descent on the difference between their product UI and the actual rating matrix R. Another application is to adjust the weights in a parallel model, right? You can have a holdout set on which you compute the error, and you just tune the weights until you get a distribution that sort of does best on the holdout set. Yeah, and what we've talked about so far is evaluating the quality of scores you predict, but in some cases, the data you collect doesn't have scores in them. They only have classifications, right? Like they're very discrete labels that say, okay, in this set of items, the user clicked item A. So in this case, you're more concerned about the accuracy of your system as opposed to the quality of the scores, because you don't really have a numerical label there, right? You just care about how often, you care about information like how often is your model clicking, is your model predicting the one that the user would have clicked, or like how specific are its recommendations to the user, right? This is where these classification metrics come in. Now, one very naive way to do this is just to compute the accuracy, as in like how often does your system predict the correct item. But the problem with that is that you might have imbalanced classes, as in like imagine if you built a system that classified if cars were electric or gasoline cars, right? You can get, your model might get an accuracy of 99% just by predicting gasoline cars for everything, because it might be the case where 99% of the cars are just gasoline cars. So in that case, having a accuracy as high as 99% still doesn't tell you anything about how well your model distinguishes between the two classes, right? What you're more concerned about are metrics like how specific are its predictions, right? So it shouldn't be predicting one class all the time. It should, you want it to be predicting, you want it to be making sensitive and specific predictions, right? That's the trade-off that we're usually looking at in these classification problems. Sensitive means that it can detect positives when they are positives, and like it detects most of the positives that are present. And specific means that most of the things that it calls positives are actually positives, right? So the way to quantify this is usually with precision and recall. So here we first define this hits. It's just a count of how many outputs are actually correctly recommended, right? This is actually this is just the numerator in your accuracy score. It's like the number of correct predictions. So precision is the number of correct recommendations over the set of recommendations your system makes, right? So this is the fraction of recommended items that are relevant, and it sort of measures how precise your system is. And recall is the number of correct recommendations over the entire set of correct items, right? So this computes what fractions of correct items are actually recommended. So that sort of tells you how sensitive your model is to correct items. And the reason there's a trade-off between this is you can imagine a system that only recommends one item. It only recommends the item that it's most confident is a correct recommendation. Right, in that case, you'll get one hit, but you'll most likely get one hit, right? Because it's like the one item it's most confident in, and it's probably right, unless your system is just is even wrong in the most confident case. So let's just assume the one most confident item is correct, and you have a recommendation set of also one, right? Because you're only recommending one. In that case, your precision is one. It has a perfect precision. But if you look at the recall, your test set could be huge. You could have a lot of potential correct items, but only recommended one. So you'll get a terrible recall score. On the other hand, the model can perfect its recall score while getting a terrible precision. And the way to do that is just to recommend all items, right? Then obviously, if you recommend all items, you'll get number of hits equal to your test set, because for each correct item you recommended it, and basically you recommended all relevant items, and you'll get a recall of one. But for the precision, you only have a limited number of hits, whereas you recommended way more items than are relevant, so your precision is terrible, right? So the way to quantify this trade-off is to use the F1 score. Like I said before, this trade-off you can recommend everything to get a recall much better than precision, or you can recommend only one thing, one most confident item, and you can get a precision much better than recall. So you want another metric that combines these two metrics, and it should tell you, and it should penalize you for favoring one of recall and precision significantly more than the other. And this is the F1 score. It takes the harmonic mean between P and R. Now, you can imagine, like, if you just took the mean between these two, you can also get a sort of combination of them, right? But why the harmonic mean? Well, the reason is that the harmonic mean places more emphasis on the worst metric, right? So if your model is doing very well in recall but terribly in precision, then that will hurt your F1. And then like doing a little bit better on the precision on the metric that you're worse in will improve the F1 score a lot more than if you did better than the metric that you're already good on. And that sort of forces your model to take a middle ground between the two metrics, as opposed to just optimizing in a way where it completely gives up on precision and just optimizes recall, because that would be, it's not useful if your model does that. It will just do one of these two things. And the harmonic mean just like, yeah, forces your model to take a middle ground between them. And you'd think that because of this trade-off, it seems like your F1 score is like bounded under a certain value, right? You can only get so good on the metrics combined, because generally doing better on one metric hurts the other. And that's why you usually will pick the threshold error prediction to maximize your F1 score, and that'll sort of be the best that your current model can do. And the only way your model can do better would be by actually improving its ability to distinguish between positive and negative samples. Because a model that distinguishes between them better, even though it still faces this trade-off, it will have like a higher bound on its F1 score. So to see F1 in practice, let's suppose your system recommends items A, C, and D, but it's supposed to recommend A, B, and C. Now the precision here is 2/3 because you have two hits. The hits are A and C, and but you recommended 3 items, A, C, and D, so your precision is 2/3. Your recall is also 2/3 because, once again, 2 hits, but there are 3 items that you're supposed to recommend, so it's 2/3. And that, when you compute the harmonic means of those, you get a F1 of 0.66. Your system can improve, in this case, in one of 2 ways. It can become more precise, in that it recommends only A and C and not the item D, which is actually not a relevant prediction. In that case, your precision will be 2/2 because you have 2 hits and you only recommended 2 items. So your system is perfectly precise. In recall, it will still be 2/3 because you're supposed to recommend A, B, and C, but you only recommended 2 of them. That's 2/3. And that gives you a F1 of 0.8. So that like improves upon the previous prediction because you dropped one irrelevant item. And it can also become more sensitive, right? And the prediction will look something like predicting all of A, B, C, and D. And the reason we call this more sensitive is, like, if you imagine the reason it didn't predict B here might have been that it had a low confidence score on B, but like higher confidence scores on A, C, and D. So becoming more sensitive means like you drop the threshold, like you require less confidence to predict an item. Like you'll predict that you're sensitive as in you'll predict something even if you have a low confidence in them. And that'll result in recommending A, B, C, D. And the precision here is 3/4 because you have 3 hits, A, B, and C, whereas you recommended 4 things, so it's 3/4. And the recall is 1 because you recommended every single correct item. That gives you a F1 of 0.86, which also improves on the previous system because you managed to predict more correct items. Yeah, and for the F1 score, usually you'll have to pick a threshold for confidence that corresponds to a positive prediction, right? Because like generally your model will, like for an item, your model will probably predict something like a number between 0 and 1, like after the softmax. You can interpret it as a probability that your model thinks this item is a positive, as in like it should recommend it. But it's still up to you to pick this threshold. And the reason for that is you might want your model to make more predictions or less predictions. And if you increase the threshold, it'll make less predictions, but you'll be more confident in the predictions it makes. And if you lower the threshold, it'll make more predictions, but it'll also be recommending less confident and generally less relevant items. All right, so usually you'll pick the threshold to maximize your F1 score. But if you think about it, if you really want to measure your model's ability to distinguish between items, the threshold you pick actually shouldn't matter that much, right? Your model essentially, if there are two classes of data, you can imagine there being a number line between 0 and 1, and your model just sort of maps positive and negative points across this number line. And you would want to have a evaluation metric where your model gets a higher score for like distinguishing between the positives and negatives more. So if most of the negatives are on one side and most of the positives are on the other side, your model should get a high score. And you don't really care where the dividing line is, because what you want to measure more is the ability to distinguish between the things. And that's what brings us to the ROC AUC. ROC stands for Receiver Operating Characteristic Curve, and AUC just refers to area under curve. And let's first go over what this curve plots. So the intention is to measure the ability of your model to distinguish between classes. And the way let's first talk about how you draw this curve. It'll sort of shed some light onto why it's drawn this way. So for your model, you'll pick a random threshold, and you'll evaluate two things, the true positive rate and the false positive rate. So this is similar to precision and recall, except one, true positive rate is of the positives, how often are you predicting that they're actually positive? And then false positive rate is how often you're predicting a false positive out of false positives plus true negative. Yeah, how often are the things you predict as positive false positives? Yeah, so you want the true positive rate to be high, but you want the false positive rate to be low. And the trade-off between these is similar to precision and recall. In fact, I think true positive rate is precision, and false positive rate, it's not recall, but there's a similar trade-off between these two things. Yeah, so you'll pick one threshold. Let's say your model predicts scores between 0 and 1. So you might pick 0.5 as your threshold, and you'll evaluate the TPR and FPR using 0.5 as the threshold. So maybe you get 0.8 as the true positive rate, you get 0.4 as the false positive rate, and you'll plot a point here. And you'll do this for a bunch of different thresholds, right? So you can sample thresholds uniformly, maybe you'll pick thresholds 0, 0.1, 0.2, and so on, and just plot 10 points on the graph. When this will generally form a curve like this. And I'll explain later why the curves are guaranteed to look concave as opposed to having dents in the middle. Yeah, so when you sample enough thresholds, it'll form a curve, and the AUC is just the area under that curve. And I'll explain why a higher AUC means that you're better able to distinguish between the two classes. Now, the reason the curves will look like this is because if you think about what you're doing when you're increasing the threshold, when you increase the threshold, your model will make less positive predictions. So it's like guaranteed to drop your false positive rate because it's just making less positive predictions, but it's also guaranteed to drop your true positive rate because you're also making less positive predictions, right? So actually, no, it's not guaranteed to drop your true positive rate. It's more likely to increase your true positive rate because when you increase the threshold, the items that you are no longer recommending are the least confident out of the true positive, are the least confident out of the positive items, right? So you'll end up with more positive. So the positive class that you end up predicting will have higher confidence scores, and therefore you should expect a higher true positive rate, right? So when you increase the threshold, the points on the graph will go in this direction. You're dropping the false positive rate, and your true positive rate is also decreasing, right? So you end up with a curve that is strictly concave. And like by the same reasoning, if you have a random classifier that just uniformly outputs a probability between 0 and 1, irrespective of the input, you'll get a straight line that's on the diagonal, and that'll give you an AUC of 0.5, which is the worst you can get. The reason you can't get worse is if you imagine you have a curve that like goes below the diagonal, you can just flip its predictions to like just flip the curve above the diagonal, and then you'll get a better AUC than 0.5. And also, if you think about what a perfect classifier does, a perfect classifier is able to completely separate the negative and positive classes on the number line. So there is a threshold where you're making, there is a threshold where you can cut the two classes so that one side is all positives and one side is all negatives. Then you'll get a false positive rate of 0 and a true positive rate of 1. And your curve will reach this corner of the graph, and that gives you an area under curve of 1, because like you're covering all of this 1 by 1 square. Yeah, and that's basically why AUC represents how well your model distinguishes between the two classes. And this way you also don't have to pick a specific threshold to evaluate it on, because like each point in this curve corresponds to a threshold, and all you care about is how well it does across all the thresholds, not how well it does for a specific threshold. There are some other metrics covered in the textbook that are specific to recommendation systems. So there's like user coverage, what fraction of users you're making recommendations for, catalog coverage, what fraction of items you're able to recommend, and then intralist similarity. This is an interesting metric because you might want to use this metric to enforce diversity constraints on the items you're recommending, right? You don't want to be recommending the same item or very similar items multiple times in the list, right? So what this metric does, it just like computes the pairwise similarity scores in your list, and you might want your model to give a low score for this, because a low intralist similarity would mean that you're having a more diverse set of items in your list. Yeah, and that covers the like topics we wanted to talk about today. They're not super complicated. There's also the like very general concepts like F1 and AUC. If you do machine learning, you'll probably run into these, even if it's not recommendation systems. Yeah. So for the rest of the lecture, we'll talk about this paper from Google that describes their YouTube recommendation system. This is probably a previous iteration of it. They probably changed it afterwards, but like it gives you a pretty good idea of how the things we talked about so far are used in practice. The paper is called Deep Neural Networks for YouTube Recommendations. So the way they formulate recommendation is as a classification problem. they pose recommendation as an extreme multi-class classification where the prediction problem becomes accurately classifying a specific video watch at a time among millions of videos. So the way to interpret this is it's not actually just asking you, okay, given a set of videos, which one is the user going to watch? It's not just classifying that. No, it's saying that if you pick a specific time where the user is watching the video, how likely is a particular video going to be watched at that time? So the subtlety there is that if the user watches a video for longer, it's more likely that you'll find that video, that they'll be watching that video at a random time you choose while they're watching, right? Like if a user has a 50-minute watch session and they spend the first 40 minutes on video A and the last 10 minutes on video B, and if you pick a random time at which they're watching, there's a 4/5 probability that they were watching video A, and only 1/5 probability that they were watching video B. And so this way, the reason they want to classify it this way is that they want to favor the videos that keep the user engaged, as opposed to click counts, right? If you didn't consider the watch time and just try to classify which videos the user clicked, then you'll be kind of giving an advantage to clickbait videos that the user just clicks in and immediately exits. And if you're not familiar with what this formula does, what's on the right side is basically just a softmax of the dot product between V and U. So V is a embedding for the video, U is an embedding for the user. This just means the predicted probability of the user watching that video at a specific time is first you compute the dot product between the user and video embeddings, and then you take the softmax of that, right? This taking the exponential and then dividing the sum of the exponentials. This is just the softmax. Most of the important things is this VI times dot product U. Yeah. And the architecture they have for this system is they separate the recommendation process into two parts. They have a part that generates candidates, and they have a part that ranks the candidates, right? So they have a large video corpus of millions of videos. They're unable to rank them together, right? Because if you want to rank all of them, you'll have to send millions of videos through a neural network every time a new user wants to get recommendations, right? So the first send it through a candidate generation system that uses k-nearest neighbors to extract a few hundred of videos that are then ranked down to a dozen. They're ranked, and then the top ranking ones, which are a dozen of videos, will actually get recommended, right? And the other advantage of doing this, other than making the computation feasible, is that at the ranking step, because you have less candidates, you can introduce more fine-grained features about the video and the user, right? So for example, if you wanted to include graphic information from the videos, if you wanted to actually learn some features from the content of the video, then it's not really feasible to do that for all the millions of videos, but it might be feasible to do that for hundreds of videos, right? So for the candidate generation part, you rely on very coarse features for the videos, and you do a k-nearest neighbor to extract a few hundred of videos, and then on those videos you use more specific features, and you're able to introduce the user features here as well. So for the candidate generation network, you generate a embedding for the user, and then use user embedding to query the set of video vectors for the top in candidates, right? And the information you include in the video, in the user embedding are like what videos you watched in the past, what you have searched in the past, and then like where you're from. So like the geographic embedding, and then your gender, your age, all the user information is encoded, at least concatenated into this large vector. And then you do a few projections to actually project to the size of your user embedding. It only says ReLU here, ReLU, because the activation is ReLU, but there's actually a fully connected layer here. So a linear layer that just projects down to this dimension, then it goes to the activation function and it gets projected again and projected again. So you can think of this as a generalization of something like content, a normal content-based retrieval system. Because like it's still using k-nearest neighbors to retrieve the similar items. It's just that the way it's generating this user embedding is non-linear, right? It can, because like imagine, I don't think a linear function is able to really extract the useful information from features this this complex, right? They're also like very from different these features are also from different modalities, so you'll probably need more non-linearities to actually encode them into an embedding that is useful for the retrieval. Yeah, so you combine a bunch of different features, you send them through a nonlinear function, and then you end up with embeddings that allow you to do retrieval. Obviously, like you optimize this later so that it actually makes embeddings that are useful. Yeah, and then the scoring model. So you retrieve a few hundred videos from the k-nearest neighbors, and then to actually narrow that down further to the few dozen of videos you recommend, you'll use this, they use this scoring model, which takes some more fine-grained features about the videos, right? So they take in the video IDs, they take user language, video language, and one important feature that they introduce is the time since last watch, because like this, this is probably a stronger indicator that the user will watch or not watch a video compared to most other features that aren't specific to the user. And this is also the reason why you separate the scoring and candidate generation model, right? Because the video embeddings here are global, so they're the same for each user, and you just have this set of video embeddings, and the only thing that's different about each user is their own embedding that's used to retrieve these video vectors. But during scoring, you can introduce user-specific features like time since last watch. If you wanted to do this for candidate generation, you'll have one data point, one time since last watch for each user and each item, and that's just infeasible to encode into all these embeddings, right? So if you want it to be user-specific here, you'd have one video vector embedding for each video for each user. Whereas if you separate the two, you only need a global video embedding. And then only at the scoring part do you introduce user-specific features. And yeah, and the number of previous watches. Actually, I think impression here means number of times they've seen this video recommended previously. So obviously, like if they've seen it a lot of times and never clicked on it, it's also a strong indicator that you shouldn't recommend it again. And for both of these features, they input the feature itself, the square, and also the square root. And this they explain is because it might want to learn sublinear, linear, or superlinear, quadratic relationships between these two features and the output scores. Yeah, and the architecture is similar. It's a few further layers with ReLU activations, and you end up predicting a score for each of the videos that are being scored. Right. But remember what we said about the loss function that they're using. They want to predict the probability of them being watched, but they're weighted by the time that the user actually spends on watching these videos. So how do we model this relationship in the loss function? Because if we just applied a normal classification loss, like cross entropy, it'll give the same weights to all the videos, right? So how do we make it so that they're weighted by watch time? Well, you'll basically give you'll give the positive samples a weight proportional to the observed watch time, and negative samples will receive unit weight. And this, they explain, makes it so that the learned odds that you predict are proportional to the expected watch time. And like an intuition that you can have about why this works, or at least why the math works out, is like, let's imagine if we just copied, like if you have video A and video B, you watch video A for 15 minutes, you watch video B for 10 minutes. You only have 2 data points here, right? One data point says the user clicked video A, one data point says the user clicked video B. So you're unable to distinguish which one should be predicted with a higher probability. But imagine if you just copied the data point for sample A you copied it 5 times, right? And then B remains the same. If you have 5 copies of the video A data point, then your model will learn to predict that with higher probability, right? Because like in this data distribution, if you randomly sample a point, there just is a 5/6 probability that the data point you choose is from A, right? And that reflects the watch time relationships, and that's basically what weighing the terms in cross entropy does. And to look more specifically at the features and what these features do, the example age feature they showed is actually very important to allowing the model to capture the relationship between watch time and the video age, right? So on the baseline model, which doesn't know about the age of a video, it's not able to capture this very strong correlation between the video age and watch time, right? This green line is how users actually behave in practice. So they click a video a lot when it's in its like first 5 days of upload, and then it gradually decreases to a steady rate afterwards, right? But once they introduced the example age, the model also caught on to this trend. See with this red line. They also did an ablation study of what happens when they remove certain features. All right, if they only look at watches, the performance is worse than when it has watches and searches, and that's worse than watches, searches, and example age. And when they include all of the features, they get another performance boost. And yeah, the paper, I think I'll post a link. You can also just search it up. I think it's a good example of how the things we talk about, machine learning and recommendation systems related, how these combine into actual systems in practice. And you can see a lot of, you can see like just everything coming together. There's like the architectures we talked about. There's like retrieval methods, k-nearest neighbors. No, not k-nearest neighbors, it's just nearest neighbors. And like ideas like embeddings, and like activation functions and stuff, softmax, cross entropy loss. You can see them like how they're actually combined in practice to produce like industry, I guess like previously industry level recommendation systems. Yeah, that'll be it for the lecture for today. There won't be an assignment this week because like for the past few weeks people have been caught up by midterms and stuff. So the submissions were pretty low for the last 2 weeks of assignment. So like we'll open up the submissions again. And like since we haven't released the solutions, I think it's okay that we extend the deadlines. And if you miss those 2 assignments, you guys can just like do them and submit them. Yeah.